We're now going to take a look at the EX15 project in my Java 8 folder in my Live Lessons GitHub repository. And this example is going to show the limitations of using inherently sequential Java streams operations, such as the iterate and limit operations, in the context of parallel streams. And it's also going to show how to overcome these limitations by using other Java stream operations that are more parallelism friendly. So let's take a look at the program. It's going to have a certain number of times it's going to run the test. We're going to set it very high to 10 million. And then we're going to have the main entry point into the program, which is going to allow us to override the default iterations. We're just going to keep it with 10 million, though, in this case, but we could always override that. We then make ourselves a new instance of the EX15 class, which is what we're going to be doing the tests. We warm up the thread pools so that we end up with results that are consistent. And then we go ahead and run several different tests. And you're going to see that there's two different variants of tests. We're going to do one that's going to use these inherently sequential Java streams operations, which work with parallel streams, but they really want to be used with sequential streams. So we're first going to try running those both sequentially and in parallel, and you'll see what the consequences are of that. And then we're also going to have another pair of tests we're going to run both sequentially and in parallel, which will be a different way of computing the same results that we're doing with the inherently sequential operations. And you'll see how much better they perform than the sequential ones do. So let's go ahead and take a look first at the test stream iterate method. And this is what this method does. It's going to use a stream and the stream iterate factor method operation to compute the square root of the first number of even numbers. And in this case, we're going to have a large number of even numbers. We're going to have, as you can see here, 10 million of these things. And if the parameter is set to the Boolean parameter called parallel is set to true, it'll use a parallel stream. Otherwise, it'll default to using a sequential stream. So let's go ahead and take a look and see how this test runs. The first thing we do is we run the garbage collector so that we can start out with a consistent memory availability for all the tests. And then we set ourselves up a little computation. And I define this using a runnable lambda, just so I can kind of make the rest of the code a little bit cleaner and not have to indent things quite as far. So you're going to see here, we start out by using the stream iterate factor method. And what that does is it's going to take an initial seed value of 2, and then it's going to have a lambda, basically an increment method, that's going to add 1 to the previous value. So effectively, it's generating an infinite length stream starting at the value of 2. Now, if it turns out that the parallel parameter was set to true, we're going to turn this stream into a parallel stream. Otherwise, it'll just stay the sequential stream, which is what it does by default. We then go ahead and take the stream, which by at this point is either parallel or sequential, and we're going to get rid of all the odd numbers. So you can see we have this method reference called isEven, and down here, this method reference is going to check to see whether the number is odd or even by using a bitwise operator to determine if the number is odd or even. And then we're going to go ahead and do the rest of the stream. And you'll see here that the approach we're going to do is going to limit ourselves to whatever max number is, which in this case is very large, but we're limiting it to that so it doesn't run forever. And after we come up with 10 million even numbers, we're then going to go ahead and compute the square root of all of them, and we're going to store the results into a list, and then we're going to check to make sure the list is actually the size that we expect here. So that's the first method family we're going to take a look at. You can see there's both versions that are sequential and parallel by passing in either true or false. The next approach we're going to do is a different way of computing the same result. This is going to be more parallelism friendly, as you see when we run the program. And this is called test stream range. So test stream range has the same parameters. It takes Boolean and a max number, but it performs the computations a little bit differently. And so what we're going to do here is, in this case, we're going to garbage collect first, then we're going to run the computation, or we're going to assign the computation to a runnable using a runnable lambda. And in this case, we're going to generate a stream of numbers from the max number times 2 plus 1. So this is going to be a very large range. It'll be essentially 20 million plus 1, starting at 2. And then once again, we conditionally decide if we want to be in parallel or not. And then in this case, what we're going to do is we're going to go ahead and do the filter operation here to get rid of all the odd numbers, just like we did before. Once again, we're going to compute the square root. Let me just show you the square root. Here's the square root method. It just basically forwards to the math square root method. Nothing tricky there. And once again, we take the results, which should be the square root of the first, in this case, 10 million even numbers, and we collect that into a list. Now, in both cases, we've got these lambdas, and then in both cases, we're going to pass them to a little helper utility I wrote that's called run timer, and I can use this to time the results of operations. So this will basically take the computation, which in this case is a runnable, and it'll figure out how long it took to run. So if we look at time run, you can see it starts the timer, runs the run method, stops the timer, and then it stores the name of the test and the time it took to execute into this hash map. And then later, as we'll see, we can print the results out and see how they compare. And in this case, the name I'm going to pass in here is either parallel or sequential stream using int stream range. And if you look up here in the test stream iterate, you see we do the same thing, except this time it's either parallel or sequential stream using stream.iterate. So let's go ahead and run the program. And I think you'll see that we get some interesting results. So now that we've looked at the code, we're going to go ahead and run the program and see what the results are. So we go ahead and click the green arrow and the processing starts. And you'll see that the stream iterate version that's using parallel streams is going to take a while to run because that's really slow. And the other ones won't take nearly as long to run, but the time here is limited by the one that takes the longest time to run. So everything's off cranking away. So you can see that the results are printed out here in essentially ascending order from fastest to slowest. So the parallel int stream range method ran the fastest, which is not a surprise. The sequential stream using the int stream range ran the second fastest. And both of those were much faster than the iterate versions. But what's most interesting here is that the parallel stream using stream iterate is by far the slowest. And what that's demonstrating is that even though you can use things like iterate and you can use things like limit with parallel streams, in other words, we get the right results, the effect is rather laborsome and has a lot of overhead. And that's because those mechanisms really are not intended for use with parallel streams. They're really intended for use with sequential streams. And you can see here that when you're in a situation where you're tempted to use iterate or limit, try whenever possible to avoid using parallel streams and instead think of different mechanisms to achieve the same result, as we did here.